In our online class on Tuesday, we learned how to solve separable differential equations. And during that class, we worked through two examples where we were able to find a solution in explicit form. And in this video, I work through an additional example where it is not possible to determine the solution explicitly. And so that all looks a little bit different. And so I wanted to create a video to show you how that looks like. So we, just a recap here, we are working on separable differential equations at the moment, and those are equations that can be written in a specific form where we can separate independent and independent variables. And so first of all, actually, let's remind ourselves that y here would be the dependent variable, and t is the independent variable. So if on the right-hand side you can separate the whatever you've got on the right-hand side, if you can separate that into a product of a function of t and a function of y, or you can write it as a fraction where the numerator is a function of t and the denominator is a function of y, or the other way around, then we have a separable differential equation. And so remember that for a differential equation, we need to find a function. So we seek a function. In this particular case, we're looking for y as a function of t that satisfies this differential equation. So satisfying this differential equation, DE, that stands for differential equation. So you'll see that the solution method is, first of all, to separate those variables. And so you can see that here I've got the dependent variable on the left-hand side and the independent variable on the right-hand side. And actually I can do the same thing for the second form. Okay, and so what we've done here is we've got the dependent variable on one side and the independent variable on the other side. Okay, so we've written that in differential form. That equation is kind of meaningless. It only has meaning if you integrate both sides of the equation. And so that's what's written in step number 2. And then, of course, you need to evaluate two integrals, the one on the left and the one on the right. And in general, the result is an equation that defines y implicitly as a function of t. And if possible, then you do a third step, namely to solve for y explicitly in terms of t. And so the examples 1 and 2 done in class allow for step 3. Okay, but in this video I want to work through an example where that last step is not possible. So the example, I've got this on the next page here. So this is, I'll call it example 3. And it is to solve the separable differential equation dy dx is equal to a fraction. And in the numerator we've got e to the y times sine squared x. And in the denominator we've got y times the secant of x. Right away, let's identify this is the independent variable and y is the dependent variable. Okay, so we seek a function y of x satisfying this differential equation. Okay. So the first step is to separate the variables, and so I'm going to put all the y's on the left-hand side. And so, actually it's easier if I do a y in the numerator, e to the y in the denominator times dy is equal to sine squared of x over the secant of x times dx. That equation in itself is meaningless until you integrate both sides. And now I'm going to rewrite both of those because neither of those we're going to evaluate as written. So the one on the left hand side, I'm going to rewrite that as y times e to the minus y dy. And on the right hand side, I'm going to rewrite this as sine squared of x times the cosine of x dx. And on the right hand side, that is because the secant of x is 1 over the cosine of x. Okay. So now we've got two integrals to evaluate. I'll call this first one here 1, and the one on the right hand side, I'll call that one 2, and we'll do them separately. So let's focus on the first one. So for 1, I think you'll all see that we need to use integration by parts here with u equal to y, and if u is equal to y, then du is equal to dy, and dv is equal to e to the minus y dy, and that results in v being equal to minus e to the minus y. And so then that integral y e to the minus y dy, by integration by parts, it becomes uv, so that's minus y e to the minus y, minus v to u. Well, v is minus e to the minus y, so that becomes plus e to the minus y there, and then times du, which is dy. Okay, and then we evaluate that last integral, so we get minus y e to the minus y minus e to the minus y plus a constant of integration. Okay, and then let me factor out an e to the minus y, so this becomes minus e to the minus y times y plus 1 plus that constant of integration. All right, so we've evaluated the first integral. Now for the second integral, I hope that you will see that you can use substitution here. So here we'll use substitution. U is equal to the sine of x, and that's because the derivative of the sine of x is the cosine of x, and that's sitting right there. So du is the cosine of x dx. Okay, so then that integral sine squared of x cosine of x dx becomes the integral of u squared from the sine squared, and the cosine of x dx becomes du. Oh, that's a nice integral to do. So that's just an easy one. That's just 1/3 u cubed. Again, plus a constant of integration. Actually, let me call this one C2, and then I'm going to go back, and the first one, from the first integral, I'm going to call that C1. And so we have to go back to x's, so this is 1/3 sine cubed of x plus that C2. All right, so now we have enough information to return to the left side of the page. And so the first integral evaluated to minus e to the y, e to the minus y, times y plus 1, plus that first constant of integration. And on the right hand side, I have 1/3 sine cubed of x plus C2. Let's multiply everything by minus 1, and let's bring the C1 over to the other side. So this becomes e to the minus y times y plus 1 is equal to, and I'm also multiplying by minus 1. So that becomes minus 1/3 sine cubed of x minus C2. Now I'm subtracting C1, but I'm multiplying by minus 1, so this becomes plus C1. Now, if I've got a jumble or a combination of constants, that's just another constant. So let's just call this C. So let this combo of constants be equal to C. And so what do I have then? I then have e to the minus y times y plus 1 is equal to c minus 1/3 sine cubed of x. Okay, and this is my general solution to the differential equation. It's defined implicitly. Okay, so this is the general solution defined implicitly. I cannot solve for y explicitly, so cannot solve for y of x explicitly. Okay, but you still can find the value of the constant of integration by applying the initial condition, and that is what we're going to do on the next page. Okay, so I still have to determine the constant of integration. So this is what we found on the previous page, that e to the minus y times y plus 1 is equal to that constant of integration c minus 1/3 sine cubed of x. And so to determine c, we apply that initial condition that y at pi over 2 is equal to minus 1. And that, of course, says that when x is equal to pi over 2, y is equal to minus 1. So we're going to substitute that into the general solution. To give the following, that e to the, well, y is equal to minus 1, so I get minus minus 1, so that's 1, and then y is minus 1 plus 1 is equal to c minus 1/3 times the sine cubed of pi over 2. Well, on the left-hand side, of course, we've got 0, and on the right-hand side, well, the sine of pi over 2 is equal to 1, and so if you cube that, you still get 1. And so we end up with an equation that says that 0 is equal to c minus 1/3, and of course that then is equivalent to saying that c has to be equal to 1/3. So therefore, the specific solution y of x is given implicitly by the following, by e to the minus y times y plus 1 is equal to 1/3. And I can actually, if you look in the box at the top of the page, we've got a 1/3 for the c, and then there's a 1/3 sine cubed x, so I can factor out a 1/3, and I'm left with a 1 minus sine cubed of x, just like that. All right, so there is my specific solution. This is a little bit unsatisfying because we can't plot, so we cannot plot this solution or this function. Okay, but we can verify that this is indeed the solution. So, and that makes a nice connection back to the previous topic in our course in chapter 9 about multivariable functions. And so I'm going to go through that on the next few pages. So we can verify that the solution is correct. Okay, so let's do that. So this is the solution, the particular solution that we found on the previous page. And we actually have two options to verify that this solution indeed does satisfy the original differential equation. So the first option is to use implicit differentiation. So we know that from the first calculus course, we differentiate both sides with respect to x, and we keep in mind that y is a function of x. So when we do that, on the left-hand side, we have to use the product rule. So we'll get e to the minus y times the derivative of y plus 1, which is dy dx, keeping in mind that y is a function of x, plus the derivative of e to the minus y. So that's e to the minus y times minus dy dx. And we leave the term y plus 1 untouched. And on the right-hand side, we differentiate with respect to x as well. And so the derivative of 1/3 is 0, and the derivative of minus 1/3 sine cubed is minus sine squared of x, because the 3 and the 1/3 cancel out, times the derivative of the sine by the chain rule, and the derivative of the sine of x is the cosine of x. And so we can simplify. So this implies that, well, on the left-hand side, let's factor out the dy dx, and I'm left with e to the minus y. I can factor that out as well, actually, and then what I'm left with is 1 minus y minus 1 is equal to minus sine squared of x times the cosine of x. These ones cancel out, and then I have a minus y e to the minus y dy dx is equal to minus sine squared of x cosine of x. And then last but not least, we can isolate dy dx, and so that is sine squared of x cosine of x over y times e to the minus y. And if you rewrite this, you can put the e to the minus y from the denominator, flip it up to the numerator, so then you end up with e to the y over y. We leave the sine squared of x in the numerator, and cosine of x, we can rewrite that as 1 over the secant of x. And so that pops a secant of x in the denominator. And this is exactly the differential equation that we started with. So indeed, our solution is correct. Okay. But of course, we had a fancier way of calculating dy dx by taking advantage of our knowledge of partial derivatives. And so I'm going to do that on the next page. So this here is option 2, is to define a new function, capital F of x and y, that is the difference between the left and the right hand side of the solution. So e to the minus y times y plus 1 minus a third times 1 minus sine cubed of x. And so the solution is given by setting capital F of xy equal to 0. So remember that to find dy dx, we have to find two partials. So we find a partial derivative of capital F with respect to x. So if we differentiate with respect to x, well, the first term, e to the minus y times y plus 1, doesn't depend on x, as far as x is concerned in this particular context. And so we just take the derivative of the minus 1/3 times 1 minus sine cubed x, and you end up with sine squared of x times the cosine of x. And if we take the partial with respect to y, they are now treated as two independent variables. And so we only have to differentiate the first term, e to the minus y times y plus 1. And I'm going to leave that as an exercise, but you'll find that this is minus y times e to the minus y by applying the product rule. And so then you can form dy dx. It is minus the partial with respect to x over the partial with respect to y. If you substitute those in, you get minus f sub x. That was sine squared of x times the cosine of x. And the partial with respect to y is minus y e to the minus y. Okay, so of course the negative signs cancel out. And if we do the same rewriting as we had done before, where we flip the e to the minus y up to the top as e to the y, and we keep sine squared x, and we have a y, and we flip the cosine of x to the denominator, and that becomes a secant of x. Okay, and that is of course also then as required. Which is not surprising because we already verified this on the previous page. All right, so this concludes the third example, and you'll see that indeed this looked different and perhaps a little bit unsatisfying, right? You do all that work and you cannot find y explicitly, but that turns out to be the case quite often. And so I wanted to work through one of those examples. All right, thank you for listening, and we'll see you in the next video. Bye.